Hi, next lesson we have is 3.3 on satellite motion. Starting off with a few definitions here. So a satellite, any object that orbits around a central object, which usually is a planet or a star. Artificial satellites, anything that we've introduced into the solar system, like communication satellites, the space shuttle, the Hubble telescope, the International Space Station, and a whole bunch of space junk now. Natural satellites are moons that are orbiting planets or planets that are orbiting the sun. And geosynchronous satellites, these are satellites that orbit Earth once per day. Okay, so in the length of time it takes for us to have one day, the satellite has gone around the entire globe. For the projectile problems we worked with, there was an unstated assumption that Earth was flat. However, we know that Earth is in fact spherical, or more precisely a geoid, like we saw in a previous lesson. With this in mind, Sir Isaac Newton reasoned that some strange things would happen if one could horizontally project an object at high speeds. You can see in this picture here what happens if you could put an object really high up, like on top of this thing, whatever it is, and increase the speed at which you're firing it, eventually it would go into orbit, like you see in the picture. At low speeds, it falls towards the ground and hits the ground in quite a short period of time. At the speed of the horse, as it increases, it gets further and further away from the starting point when it hits the ground. For flat Earth, it would always hit the ground. No matter how fast the projectile went, gravity would always pull it down and it would hit the ground. However, since Earth is spherical, the curvature of the Earth affects where the projectile lands. As the diagram is showing you, the greater the horizontal speed, the more the Earth's curvature comes into play. Eventually, something called a critical speed can be reached, where even though the projectile is in free fall, it would not hit the Earth. Rather, it becomes a satellite and it starts to orbit around the Earth. So Newton was actually able to calculate the speed required to put an object into an orbit, which would just skim the surface of a smooth Earth. He realized that a satellite orbiting the sun, the Earth, or some other body is simply a case of uniform circular motion. He reasoned that gravitational force would act as the centripetal force for a circular orbit. What that's saying is that centripetal force is supplied by the force due to gravity. So we can set up this equation. Doing a substitution of centripetal forces equation and an equation for force gravity, we can come up with this next equation. What's going to happen is the mass of the satellite cancels out. That should make sense because the satellite, the thing doing the orbiting, is much smaller than the thing being orbited. So the mass of that object, like let's say maybe the International Space Station, is negligent when you think about it in comparison with the mass of Earth, the thing that it is orbiting. The thing providing the gravity, that's why we do capital M, like you can see here, it is much bigger and comes into play much more than the mass of the satellite. And in the mathematics, those masses cancel out anyways and have no effect on the centripetal force. You also end up with these two R's, or three R's more exact, that are in the denominators. If you imagine one of the R's coming up here, you could cancel an R with one here. That's what you're seeing moving into this next step. Then if I wanted to get the velocity, I would just square root, and you should see this formula sheet, or pardon me, this formula on your formula sheet in the circular motion section there. It says velocity of a satellite is equal to big G, big M over R square rooted. So what are all of these things? Big G, we remember the universal gravitational constant. It's on the back of your formula sheet. It's a number. Big M is the mass of the body being orbited, so basically the one in the center. And r is the distance from the center of that mass to the satellite. So in this section, there's a lot of adding radii to get that right number, because you need to go from the center of that mass. So the center of that mass to the outside of that mass would be the radius. And then usually a satellite is not on the surface, it's up in the air quite a ways. So you need to add that distance as well. The orbit does not depend on the mass of the satellite, as long as the mass of the planet or star is much, much larger, which it usually is. The treatment of orbits that we shall work with is quite limited. For example, to calculate escape velocities of satellites requires that we account for gravitational potential energy. In addition, we will limit ourselves to circular and not elliptical orbits. So we are kind of forcing this to work just for circular orbits, but a lot of things orbit in ellipses or elliptical orbits. It doesn't work for those, only circular orbits. So what's the speed of orbit for a satellite orbiting Saturn if the radius of orbit is 6.43 times 10 to the 7 meters? Well, you see there's not a lot of numbers. The numbers come from, in your textbook, page 218. So if you go there in your textbook, you will see a big chart like this that tells you all of the celestial bodies in our solar system, their masses, and their equatorial radii. We're going to need to use those numbers in a lot of these questions, because if we want to figure out the speed that a satellite will orbit using the equation that we just created, we need two numbers. We need the mass of the body it's orbiting, and we need the r value from the center of the object to the satellite. So what's the speed of orbit for a satellite orbiting Saturn? So in order for us to do this, we need the mass of Saturn, and we do have the r value. That's the radius of orbit, not the radius of Saturn, but the radius of orbit of this satellite. So let's go ahead and check the textbook. I need to find the mass of Saturn. So I look on the chart, the mass is 5.69 times 10 to the 26 kilograms. I now have enough information to do this question. I am going to sub in my G value from the formula sheet. It's that 6.67 times 10 to the negative 11 number. Remember, the units are quite disgusting, really. Newton meter squared per kilogram squared. Then I'm going to times by the mass of Saturn, the thing that is being orbited. I'm going to divide by the radius of orbit. And remember, all of these things have to be in the proper units. And I'm going to square root my answer. Put this in your calculator exactly how you see it, with brackets, division, and do the middle first, and then you can just square root your answer. We've talked in class about how to do that on the calculators. And you should end up with 2.43 times 10 to the 4 meters per second. That's how fast that satellite is orbiting Saturn. So let's recall now that the derivation of the formula we used came from the idea that the force of gravity is supplying the centripetal force. That's what's keeping these satellites in a circle. We have more choices for these equations. There's more equations on your formula sheet. We have good old Fg equals mg for force gravity. We've also taken a look at this big equation where we figure out the force of gravity between two objects. We have the mass of one and the mass of the other and the distance separating those two objects. We also have a couple choices for centripetal force. We can go with mv squared over r that we looked at in the last lesson, or we can go with this bigger equation that talks about the radius, the mass, and the period. So depending on what I'm giving you in the question, you're going to set up your equation accordingly. So if I'm giving you information about period, you might choose this centripetal force to sub in. If I'm giving you information about the masses of two objects that have gravity between them, you might set up with that part for gravity. So although we give you a lot of equations on your formula sheet, I prefer to teach this where you derive your own equations based off of this initial setup. Then you're going to sub in the equation that you want for centripetal force and the equation that you want for force of gravity. Then there's a lot of algebra that can be done to simplify because I know some of these equations look quite complex. So we need to pick the right ones in the next examples. Galileo discovered 4 moons of Jupiter, listed below. Also listed are their periods of revolution and their orbital radii, center to center. From this data, we need to determine the mass of Jupiter. The initial setup is always the same. What is keeping the circular motion going is the force of gravity from Jupiter. That's what's keeping its moons going in a circle around Jupiter. Okay? Now we pick the next substitution based on what we want. So for centripetal force, since we have period, I'm going to pick this equation. I picked the equation from the previous slide or from your formula sheet for centripetal force that has period in it. What should I pick for force gravity now? Well, I need something that has the masses in it and R in it. Here's a formula with the masses and R. Now let's change these subscripts. Okay, let's talk about what masses we're talking about here. We are talking about Jupiter, and we can use any of the moons to figure this out. Just because it's simple to spell, let's use the moon Io. Now I want you to think about this. In the force centripetal equation, it has a mass. What mass, when you're talking about the circular motion of an object, would be important there? What mass is moving in a circle? Is it Jupiter or is it Jupiter's moon Io? The one that's doing the circular motion, if you think about the bucket of water on the string again, the one on the outside that's moving in a circle is Io. That's the mass that you have to use for centripetal force. Now, something nice is going to happen here because we do have the mass of Io on both sides of the equation. So right away, the equation's getting much simpler. Now, what are we trying to solve for here? We are ultimately trying to find the mass of Jupiter. So we need to isolate that. The first thing I'm going to do to isolate MJ, not Michael Jackson, is I'm going to multiply by r squared. I've got an r to the 1 here. If I multiply by r squared, I'm going to get r cubed. Okay. The next thing I need to do is get rid of g. So I'm going to divide both sides by g. Now you can do that in a couple more written out steps if you need to show the algebra more completely. Or you can plug and chug, that works as well. But I find rearranging the equations, if you can try and do that without numbers, is much simpler because a lot of times, like our r's combine to be r cubed and certain things cancel. So it's a little easier just to rearrange it without numbers. Keep in mind too that all the numbers are scientific notation, so they can be quite disgusting. Okay, I need to put in R now. So my R value, my distance from the center of Jupiter to the center of Io is going to be 422, and then up here it says 10 to the 6 meters. Now, this isn't technically scientific notation because that's not 4.22, it's 422. But you can work with the number just the same. It doesn't have to be between 1 and 10 for you to put it in your calculator and make it look like that. Just put 422, press the little E button, and then 6. Now, don't forget that this needs to be cubed before we divide by G. And the period squared. Can I put that number in for my period? No, that number does not have the right units. That is telling you days. Let's go down the page a little bit because we have to make that number into seconds. That's the only way that this is going to work. The way that we do that is we do dimensional analysis. So write the number down. Put your days on the bottom so that they cancel, and think about the next smallest thing other than a day. One day has 24 hours. Days have now canceled, and we go again. 1 hour has 60 minutes. Cancel. 1 minute has 60 seconds. If I do this multiplication now, 1.7691 blah 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 times 24 times 60 times 60, I get this to be 152853.5047 seconds. That's the number that I need to use in my equation. And don't forget that it needs to be squared. If it helps you to make sure that you didn't forget any of the exponents, you can do them in a different color like this or highlight them so that you can see that you did all of those exponents. It's especially hard to kind of notice if you have messy writing. And since some of them have scientific notation, there's like exponents on exponents, which is a lot to look at. But there you have the equation. This might take a few tries for you to get it in your calculator correctly, but don't give up. Put it in exactly how you see it with brackets where you see them, and this should calculate out. The other suggestion I have for entering it in your calculator is maybe do the bottom first, and then you can just do the top and divide by your answer. That's another suggestion. If you're having calculator troubles and you're not able to get the mass of Jupiter to be 1.90 times 10 to the 27 kilograms, then you need to set up a video chat with me so I can watch what buttons you're pressing and we can get you entering this properly. Remember, we have to tell the calculator to do BEDMAS in the proper order. So if you need to enter the top, get a number, enter the bottom, get a number, and then divide those answers, that's totally fine. You just have to get used to how your calculator calculates things. And we try again. What's the speed of the moon Io based on the information in the previous slide? So we want the speed of that moon, and what's keeping the moon in a circle, again, is force gravity. That's where you always start. I want to find speed of the moon. So if I go back a couple slides, I need to pick this one according to which one has speed in it. This equation doesn't have speed in it, so I'm not going to pick that one. I'm going to pick mv squared over r. And then for force gravity, I'm going to pick the same one from before because that nifty thing happened where the mass is canceled and made it quite a bit simpler. Okay. So let's talk about what the masses are again. We've got Jupiter and we've got the moon Io. What mass would be under force centripetal? What thing is doing the circling? Again, it's Io. So the mass of Io will cancel. The mass of Jupiter is the thing that's really causing this gravity to happen because the mass of Jupiter is so huge in comparison to its moon Io. Now I want to solve for V. I'm going to multiply the R up. And I'm going to square root it. But I can simplify a little bit. There's an R on top and 2 on the bottom, so I get 1 on the bottom. And here's the formula from your formula sheet that you could have jumped right to. But why do I show you how to find the formula? Because that's a lot of really good algebra skills to have going into Physics 30. And it's really not that hard once you practice it a few times. Let's go ahead and sub in what we know. We know the G. Okay. We know the mass of Jupiter. Either from the question that we just did or from page 218 in the textbook. And we know, we used it in the last question, the orbital radius for Jupiter and Io, center to center, is 422 times 10 to the 6 meters. Don't forget to square root your answer. And we are going to get the speed of Io to be 1.73 times 10 to the 4 meters per second. And remember, we can always times by 3.6 if this was maybe multiple choice and the answers were in kilometers per hour. If it's kilometers per hour, I got a 6.24 times 10 to the 4 kilometers per hour. If you're getting the hang of this, why don't you pause and see if you can do the question on this slide by yourself, and then we'll come back together and I'll give you the solution. All right, average distance from center of Earth to center of its moon is 3.85 times 10 to the 8 meters. What is the period of orbit of the moon around the Earth? Same initial setup as every other question. What is keeping the moon in a circular orbit around Earth? The force centripetal is supplied by force gravity. The information that I have about Earth here is I have the R value from center of Earth to center of moon. I want to know the period of orbit. So I need to pick an equation for FC here that has period in it. That is this one that we used on the first question. 4 pi squared R M over T squared. Now think about this. For centripetal, the circle, what mass is going in a circle? That would be the mass of our moon is going in a circle. Now you'll notice that we just keep using this same formula for Fg because it has the masses in it that cancel. Now I've gone ahead and instead of saying M1 and M2, I've said mass of Earth and mass of moon. Those are the two objects that we're talking about here. Mass of moon cancels because it's so insignificant in comparison to the mass of the Earth. And we want to solve here for period. I want to get this by itself. First thing I'm going to do is I'm going to switch places with those two. So I've got 4 pi squared R over G mass of Earth equals T squared over R squared. If you can do this in fewer steps, that's great. The R can go up. If I've got an R times R squared, that makes R cubed. How do I get T by itself? Square root. So T is going to be equal to The square root of 4 pi squared. Could we figure that out as a number? Square root of 4 is 2. Square root of pi squared, the square root and squared would cancel and you'd get pi. R cubed over g mass of Earth. I believe we have given you something similar. Yes, we've given you that exact thing on the formula sheet, but those skills that we just used to find it by hand are invaluable. I suggest that you do not pick it off the formula sheet. You go ahead and derive your formulas for this. It gives you a lot more skills going into next year. Let's sub in now. What are they telling us for the center to center distance between Earth and Moon? 3.85 times 10 to the 8 meters. That's right from the question. Don't forget to cube it. We've got our G value. And they're asking us for the mass of Earth, which we can find in one of two places. Our formula sheet has mass of Earth, and page 218 in the textbook has the mass of Earth, 5.97 times 10 to the 24 kilograms. Don't forget to square root. Pause the video, see if you can pop it in your calculator properly. 2.38 times 10 to the 6 seconds. Pause the video, do dimensional analysis, tell me that number in days. What is the dimensional analysis for this? 2.38 times 10 to the 6 seconds. There are 60 seconds in 1 minute. There are 60 minutes in 1 hour. And there are 24 hours in 1 day. Canceling any units on top and bottom and multiplying this out, remember put these in brackets when you divide them, is going to give you a number that sounds just about right. What is the orbital period for our moon around our planet Earth? Does 27.5 days make perfect sense? Orbital period, amount of time it takes our moon to do 1 lap around Earth. How long does it take for us to go from full moon to full moon? It's about 27.5 days. One last question. Determine the height from the surface of the Earth of a geosynchronous satellite. Weird question because there's no numbers, so that's crazy. But we actually do have every number between our formula sheet and our textbook to do this. The key to this question comes in the definition of what a geosynchronous satellite is. If you want to pause the video, the definition is on the first slide. A geosynchronous satellite orbits once per day. So when we say it like that in English, it orbits once per day, what are we actually saying? We're saying the period of orbit is 1 day, or the T is 1 day. But I cannot use those units, days. I need to use seconds. So I go ahead and I say 1 day has 24 hours, 1 hour has 60 minutes, and 1 minute has 60 seconds. I get the number of seconds in 1 day to be 86,400 seconds. That is my period. That is how long it takes a geosynchronous satellite to orbit the Earth. Let's set up our equation. See if you can do this one on your own. We want to figure out the height from the surface of Earth. That's going to have something to do with R. So I want to pick a formula for centripetal force that has R and T in it. Looking on my formula sheet or a previous slide, I see that this formula has both T and R in it, like I want. Now, what's going in a circle? The satellite or the Earth? It's the satellite that's going in a circle. We have the Earth and we have a satellite at play here. Just like we've done, the mass of the satellite is going to cancel. We can rearrange this. We want this time R. So this is a rearrangement we haven't quite done yet. I'm going to go ahead and I'm multiplying both things up. So we just have numerators. That's going to give me 4 pi squared r cubed equals g, mass of Earth, and t squared. Now that I've got just numerators, I can isolate the r's by dividing by 4 pi squared. Cancel, cancel. R cubed equals all of this stuff. How do you get rid of cubing something? Well, you cube root it. So R is equal to the cube root of g times mass of Earth times period squared over 4 pi squared. Do some people forget to cube root and do the square root instead? You bet. If we give multiple choice questions, that's probably one of the calculations I do to get a distractor. Remember, all the distractors in multiple choice are from common errors that students might do. Let's sub our numbers in now. G, the mass of Earth on my formula sheet, also in the textbook. The period that I calculated above in seconds squared. I might highlight that if I am worried about forgetting it in my calculator. Divided by 4 pi squared. Remember, don't you dare put 3.14. That's not what pi is. Pi is a button on your calculator. You need to use it. I'd maybe calculate the numerator. Okay, have that sitting on your calculator screen. Then I would hit divide 4 pi squared so that my calculator takes answer, divide 4 pi squared. And then I would cube root my answer. So it might look like this. Answer, divide 4 pi squared. Okay, and then cube root the next answer. Try it until you're able to come up with 4.2 times 10 to the 7 meters. Now think about what that is. We set this equation up to talk about the satellite and the Earth. The R value when you're talking about this with circular motion is from the center of the circle to the satellite. So this goes from the center of the Earth to where this satellite is orbiting Earth. Is that what the question's asking for? No, the question is asking for the height above Earth. That is not R. R goes all the way to the middle. It includes the radius. So how are we going to get this to be height above Earth? We're going to take that number and we're going to subtract the radius of Earth. Okay? The radius of Earth from your formula sheet is 6.37 times 10 to the 6 meters. So take your previous answer and minus that. 3.59 times 10 to the 7 meters above the surface of Earth. Or, if you want some perspective, 35,857 kilometers above the surface of Earth. So these satellites might be positioned right above us in the sky, but they don't look like they're moving because they're going around Earth in one day. which we also are doing. So if we look up in the sky and we see something that looks like a star, it might actually be a satellite that's a geosynchronous satellite that's orbiting once per day. How far away would that thing that we're looking at be if it is indeed a satellite and not a star? 35,857 kilometers away from the Earth's surface. Just for a little perspective. Of course, that last answer doesn't have the correct sig digs, but there's your good answer there. All right, lots of algebra there. So if you need any help or you want me to draw out a solution and send you a picture, just give me a quick email.